Have you ever pondered if time could freeze? If looking at a clock could stop time? It sounds absurd, doesn't it? Yet, as we delve into the fascinating realm of quantum physics, such absurdity transforms into a captivating reality. We are about to embark on a journey where time and its paradoxes take center stage. Now let's start with what we know about time. It's a fundamental part of our lives, isn't it? Every beat of our hearts, every breath we take, every sunrise and sunset, all of these are measured in units of time. We see time as a relentless river, always flowing forward, never backward. It's constant, unyielding, and seemingly unstoppable. But what if I told you that in the realm of the quantum, time could be manipulated? Welcome to the paradoxical world of quantum physics, where the rules of the macro world do not apply. Here, particles can exist in multiple states at once, teleport through barriers, and yes, even manipulate time. It's in this bizarre world that we encounter the Quantum Zeno Effect. The Quantum Zeno Effect, named after the Greek philosopher Zeno of Elea, proposes a concept that would seem ludicrous in our everyday lives. That frequent observation can halt change. Imagine looking at a pot of water that never boils, or a clock whose hands never move, simply because you're observing them. It's a mind-boggling concept, isn't it? The Quantum Zeno Effect hints at a reality where time is not as linear or as constant as we perceive it to be. It suggests that perhaps in the quantum world, time can be frozen, slowed, or maybe even reversed. It's a concept that challenges our understanding of the universe and our place within it. In quantum physics, time may not be as straightforward as we perceive in our everyday lives. So buckle up as we dive deeper into this fascinating and paradoxical world in the scenes to come. To comprehend the Quantum Zeno Effect, we must first dive into the peculiar world of quantum mechanics. This world, my friends, is a fascinating realm where reality as we know it takes a back seat and the rules of classical physics no longer apply. At the heart of quantum mechanics lies the concept of superposition. Superposition is a bit like being in two places at once. Imagine you're at home, curled up on the couch with a good book, but also at the same time, you're out for a jog in the park. Sounds impossible, right? But in the quantum world, particles can do exactly this. They can exist in multiple states simultaneously. This is the magic of superposition. Now let's talk about quantum states. Quantum states are the different configurations a quantum system can be in. Think about a light switch. It can be in two states, on or off. But in the quantum world, a light switch can be both on and off at the same time. That's right. Quantum particles don't decide on a state until they absolutely have to. This brings us to a crucial point, the act of measurement. In the context of quantum mechanics, measurement isn't just a passive act of observing. It's more like a forceful interrogation that forces quantum particles to make a decision, to pick a side. When you measure a quantum particle, you're forcing it to choose a state. This is why particles can exist in multiple states simultaneously until observed. This concept is beautifully encapsulated in the famous thought experiment known as Schrödinger's cat, where a cat in a box is both alive and dead until someone opens the box to check. So, to sum up, in the quantum world, particles can exist in multiple states at once, thanks to superposition. They don't settle on a state until they're measured, and this act of measurement forces them to choose. It's a world where possibilities are endless until observed. In the quantum world, observation fundamentally alters reality. Now let's delve into the heart of the Quantum Zeno Effect. Picture this. You're watching a pot of water, waiting for it to boil. According to the old adage, it feels as though it never does, right? This is a bit like the Quantum Zeno Effect, but on a much smaller scale. You see, in the strange and counterintuitive realm of quantum mechanics, things don't behave as they do in our everyday world. Tiny particles exist in a state of superposition, meaning they can be in multiple states at once, until they are observed. When we look at them, they collapse into one state or another. This is known as a quantum leap. Here's where the Quantum Zeno Effect comes in. Named after the ancient Greek philosopher Zeno of Elea, who was famous for his paradoxes, this effect is a paradox in its own right. It's the quantum equivalent of a watched pot never boiling. If you observe a quantum system frequently enough, it seems to freeze, unable to change or evolve. Imagine you have a quantum particle that's in a superposition of two states. Let's call them happy and sad. If you observe this particle over and over again in quick succession, you'll find that it remains happy. It's as if your constant observation prevents it from making the quantum leap to sad. But why does this happen? Well, every time you observe the particle, you're essentially resetting the clock. The particle doesn't have enough time to change before you look at it again. So in a way, you're freezing it in time. Of course, this is a simplification. The actual math and physics behind the quantum Zeno effect are far more complex. But the core idea is this. In the quantum world, observation isn't a passive act. It's a powerful tool that can shape the behavior of the tiniest particles in our universe. So, in a sense, observing a quantum system is like hitting the pause button on a remote. You might be wondering, what does this all mean for us? Well, the implications of the quantum Zeno effect are far-reaching and profound, particularly in the realms of technology and our comprehension of reality. Let's first delve into the realm of technology. One area that stands to benefit from the quantum Zeno effect is quantum computing. These are not your everyday computers. Quantum computers use quantum bits, or qubits, which can exist in multiple states at once, thanks to the principle of superposition. This allows them to perform complex calculations much faster than traditional computers. The quantum Zeno effect could potentially be harnessed to stabilize these qubits. By frequently observing the qubits, the Zeno effect could prevent them from changing states, essentially freezing them in place. This could lead to more efficient and reliable quantum computing systems. The quantum Zeno effect also has potential applications in the world of atomic clocks. These are the most accurate timekeeping devices we have, with some models only losing a second every few billion years. Atomic clocks work by measuring the vibrations of atoms, but these vibrations can be influenced by various factors. The quantum Zeno effect could be used to stabilize these vibrations, making atomic clocks even more accurate. But beyond the world of technology, the quantum Zeno effect could have profound implications for our understanding of the universe. It challenges our classical view of time as a continuous, unstoppable flow. Instead, it suggests that time might be more of a subjective perception, influenced by the act of observation. This idea could lead to new insights into the nature of consciousness and reality itself. In essence, the quantum Zeno effect shows us that the universe is even stranger and more complex than we thought. It's a reminder of the curious mysteries that still await us in the world of quantum physics, and a testament to the power of observation. The quantum Zeno effect may have far-reaching implications from technology to our understanding of reality. It's a fascinating reminder that in the quantum world, not only does the observer affect the observed, but the very act of observation can freeze time itself. So, what have we learned about the quantum Zeno effect? Well, we've journeyed through the paradox of time, delved into the quantum world, and uncovered the marvels of the quantum Zeno effect. We've seen how this strange phenomenon, named after the ancient Greek philosopher Zeno, challenges our conventional understanding of time by suggesting that observation can freeze it. Let's take a quick trip down memory lane. We kicked off by exploring the concept of time, its paradoxical nature, and its relation to our everyday lives. It's a fascinating subject that never fails to captivate, isn't it? Then, we dove into the quantum world, a realm where the laws of classical physics take a back seat and the bizarre takes center stage. Our exploration of the quantum Zeno effect was a journey into the heart of quantum strangeness. We learned that by observing a quantum system, we can effectively freeze its evolution, much like Zeno's arrow that never reaches its target. It's a notion that seems to defy logic, yet it's a reality in the quantum world. We also discussed the potential implications of the quantum Zeno effect. From quantum computing to the study of biological systems, this odd phenomenon could have far-reaching impacts. And that's the beauty of science, isn't it? Even the strangest discoveries can open doors to new frontiers of knowledge. But hold on a sec, before we wrap up, if you're intrigued by these insights into the weird and wonderful world of quantum physics, why not subscribe? We've got loads more science content that will tickle your curiosity and expand your horizons. So go ahead, click that subscribe button and join us on this journey of discovery. The quantum Zeno effect challenges our conventional understanding of time, showing us just how strange and wonderful the quantum world can be.